Okay? We're going to look at several different types of energy, most importantly, two different types. There's all kinds of different types of energy, electrical, potential, kinetic, thermal, all these kinds of different types. We're going to focus on two main types. Okay? We're going to talk about kinetic and potential energy. Okay, kinetic and potential energy. Have any of you heard those terms before? Okay, good. Basis of those two. Okay? Energy in and of itself is the ability to do work. And we're talking about physics work here. So when we talked about work last class, what's the unit for work? Joules, good. Okay? And work is force times displacement, right? We apply a force over a certain displacement. So our energy in and of itself is the ability of an object to do work. Okay? Kinetic energy can often and most of the time be transferred from one object to another. Do we remember an example in which that happened? Maybe while we were doing our collisions lab? What type of collision transfers all of its energy to another object? Elastic, good. Elastic collisions have no loss in kinetic energy, so all of that energy is transferred to another. Okay? When an object exerts a force on another object and displaces that object, we can say that work has been done. Okay, and that's the kind of basis of kinetic energy. When that first ball hits the second ball and applies a force and causes that second ball to move or be displaced, that means that the first ball has done work on the second. Okay, that's what we're thinking in terms of that collision there. Okay, and here's our equation that we want to solve. If we would like to solve for the amount of kinetic energy at a certain location, this is what we use. Kinetic energy is equal to 1/2 mv squared. What would the m be equal to? What do you think? Mass, good. And v is velocity, good. Okay, so this is kind of reflects back to our momentum chapter, right? Momentum is equal to mass times velocity. This is almost that same thing. We're doing the connection between those two as an object that's in motion, okay? And the last thing I want to point out here about kinetic energy is that it's considered translational kinetic energy, so it's not rotating, it's not spinning. Okay, these are things that are typically moving in a straight line motion, okay, but they're not spinning. Remember that the delta is final minus initial. So when we have the 2 here, that means final. When we have the 1, that means initial. Okay? And that's what we're looking at here. We can take the net work of something and solve for delta kinetic energy. So this equation right here, this top one, that should go on your equation sheet, as should the kinetic energy equation from the last slide. Okay, that 1/2 mv squared, that needs to go on your equation sheet as well. This is just telling us exactly what our equation is, right? The net work is equal to the change in kinetic energy. Like I said, this is called the work energy principle. And something that we have to pay attention to when we're looking at this equation is that it's the net overall work that's being done. It's not the work done by gravity. It's not the work done by friction. It's not the work done by the applied force. It's the overall net. Okay, so that's just something we have to think about here. Good? Okay. So looking at our work energy principle, which is the equation that we just got, we can see that if positive work is being done, okay, if the net work comes out positive, then our kinetic energy is increasing because final kinetic energy would be greater than initial kinetic energy, okay? And the opposite is true. So if negative work is done, that means we've had a loss in kinetic energy or a decrease in kinetic energy. Okay, the object has slowed down, it's transferred some of its energy, some of those things would give us negative work. Okay, if no net work is done on the object, then kinetic energy remains constant. That means there's no change in speed, that means it's just kind of going on cruise control, it's not transferring any energy, that means no work is done, right? When we move at constant velocity, we're not doing any work. That's the same thing that we're saying here. Okay. Kinetic energy is measured in joules, just like work, so that one you should probably have down, know what your kinetic energy unit is. Okay, so kinetic energy unit is joules, so it's a capital J. And kinetic energy is also a scalar. Okay, so we don't have to include a direction here. All right, let's go ahead and try a practice now. So if you don't have your calculator out, go ahead and grab that. And you can write down this problem as much as you need, but we're going to do this as a class here in just a second. So if we want to find the kinetic energy, we're going to use their equation Ke equals 1/2 mv squared. Okay, our mass is equal to 145 grams. What do we need to do to that gram? We have to convert it to kilograms. So that gives us 0.145 kilograms. Remember, 3 spaces to the left. Our velocity is 25 meters per second. So that means Ke is equal to 1/2 0.145 times 25 squared. Okay? What did we get for our final answer? 45.31 joules. Good. Do we agree with that? Okay, it's important to know that only our velocity is squared. We're not squaring the whole entire term, just velocity is squared. Okay, so there's our first question. Now it asks us how much work was done to make it reach this speed if it started from rest. That means we're going to use our work energy principle. So we're taking work is equal to delta Ke. Okay. And if it started from rest, that means that our initial velocity was what? 0. Okay? And our final kinetic energy was 45.31. Okay? Which that means that's how much work was done also. Work is equal to 45.31 joules. Okay? Because it started from rest. Work is required to accelerate a 1,000-kilogram car from 20 meters per second to 30 meters per second. Okay, so our work is equal to 1/2 1,000 times 30 squared, because that's our final, minus 1/2 1,000 20 squared. Should we have a positive network or a negative network? Positive, because we're increasing speed, which means we're gaining kinetic energy. Okay, so our car is 1,000 kilograms, our velocity final is 30, and our velocity initial is 20. Any questions about where these numbers are coming from? Okay. Do we agree? Good. Very good. Okay. Power, which is our focus of our lab today. Okay. And power is a rate. So a rate always means something over time, how fast you're doing something. Okay, so power is the rate at which work was done. Okay, so power is equal to work over time. The unit for power is watts. Where do we see watts at typically? Yeah, in light bulbs, electricity, good, okay? That's where we usually see watts at. So a watt is 1 joule per 1 second. That's where we're getting our unit from. power also has the ability to be measured in horsepower. And where do we see that at? In cars. Yeah, we see it in cars. Okay? And here's our conversion between horsepower and joules. Okay? I'm sorry, horsepower and watts. I'm sorry. So 1 horsepower is equal to 746 watts. So we're going to have to convert back and forth between those two quite a bit. So just make sure you know that conversion factor. Your number of horsepower, should it always be larger or smaller than your number of watts? It should always be smaller because there's 746 watts in 1 horsepower. Okay, so our number of horsepower should always be smaller. Remember that. Okay. And here's our equation for finding power. We're going to take work divided by the time that it took. So what should our time be measured in? In seconds. Right here it tells us it's joules per second. So we need it to be in seconds, otherwise we don't get a true watt. Okay. We have to understand that power and energy are not the same thing. Okay? Not the same thing. A person's work, okay, the amount of work that I have the ability to do is limited. Okay, the amount of work that my body can do is limited. Okay? And it depends on how much energy I expend. And there's going to be kind of a big example up here. But this is kind of how you think of it. If I'm going to sprint upstairs 2 at a time, the time that it takes me to do that is less, which means my power output is greater. Okay? So I can't do as many I can't do as many sprinting up the stairs as if I was just going to walk up the stairs. My power output would be less if I walked up the stairs, and it would be greater if I ran up the stairs, but the amount of energy that I have to do that is limited. So the amount of work that a person can physically do is limited. Okay? It's only so fast that our body can convert that energy that we need to be sprinting up the stairs. So we have a limitation. If I was going to walk up the stairs, I could go a lot higher. I could climb a lot higher, right? My power output would be less, but I wouldn't be expending as much energy, which means I could go higher and higher. Okay? Any questions there? Let's go ahead and try this one. A student uses 140 newtons to push a block up a ramp at a constant velocity of 2.2 meters per second. What's their power output? Okay, so I want you to show you this derivation of equations right over here when you get done writing it down. So you don't have to write down all of these equations. I want to talk through these before you put them on your equation sheet a little bit. Okay, so go ahead and write your problem down, and then we will get started on that. All right, so let's look at these equations over on the side here. This is our true equation for power. Power is equal to work over time. Okay, and we know that work is equal to force times displacement. We learned that last class. Work is equal to force times displacement. What does this displacement over time, what variable or what value does that give us? Velocity. So to find power, I also have the ability to multiply force times velocity. Okay? We can use any of these 3 sets of equations depending on what we're given in our problem. So if you would like to write all 3 of them down, if you'd like to write this one and this one down, that's fine. Whatever you choose, but we can use any of these 3 equations to help us solve for power. Okay, we're even going to get one more that we're going to practice with the lab today. Okay, let's go ahead and try and solve this problem now. Now that we've looked at all 3 equations, which should we use for this problem? First, second, or third equation? The third, right? Because we're given a force and we're given a velocity. Okay, we're not given the mass of the box, so we can't use kinetic energy to find work, to find power. So we're going to go ahead and use force times velocity. Power is equal to 140 times 2.2. Cole, what'd you get? 308. Thank you. All right, we could have gone ahead and solved 9 divided by 15 to just find our velocity and plug that in times our force, but we went ahead and just did it all in one equation. Our potential energy is associated with forces that depend on the position of the object. We care about how far it is off the ground. We care about how far it's moving in its path. So our potential energy is dependent upon the position of our object. And the major form of potential energy that we're concerned with and that we use most of the time is gravitational potential energy. Okay, we care about the work or the potential energy of an object to fall. Okay, we care about its potential to fall to the ground. That's what gravitational energy kind of tells us. What potential does it have to keep falling, to move down farther on its path? Okay, so when I hold an object, okay, like a brick or any object, off the ground, this has potential energy right now. It has the potential to fall to the ground. If it's sitting on the ground, does it have any potential to fall farther? No. So there it has no potential energy. Okay? When we're thinking about an object that's falling through the sky, okay, if I think about an object that's falling, is it in motion? Yes. So does it have kinetic energy? And is it off the ground? So does it have potential also? Yes. An object can have both types. So as this object is falling through the air, it's going to have both types. As it reaches like the instant before it hits the ground, it has all kinetic. As it's sitting at its highest point, it has all potential. And then as it falls, we transfer those types of energy farther and farther. Okay. When an object is falling through the air, it also has potential to do work if it falls on a specific object. Okay, so think about if you have a stake in the ground or a nail or something that you're trying to hit into the ground, and I drop something on it. When I drop it, it's applying a force which displaces that stake into the ground, which means it's done work on something. Okay, so you can think of it as having the potential to do work on an object, or you can have the potential to fall to the ground. You can think of it either way, kind of. So our equation for potential energy due to gravity, right, something that's falling, something that's hanging through the air, and this is the equation that we'll use for potential energy almost all the time, is mgh. Mass times gravity times the height of an object off the ground. Okay, the height of an object off the ground. Or from its equilibrium point, wherever that equilibrium point is. Could be on the ground, could be somewhere else, but most of the time we're looking at the ground here. Okay, so the higher off the ground an object is, the more potential energy it has. As it falls, it starts to lose potential energy and gain kinetic energy. So as it falls farther and farther, it's kind of like a pie chart. Okay, you'll see it lose potential but gain kinetic. We can also find here the work done by gravity by using our change in potential energy. So here's another equation. These two should go on your equation sheet. Work due to gravity is equal to negative potential energy, negative change in potential energy. You need this one on your equation sheet as well. You don't necessarily have to include the little g because that's the equation we're going to use 90% of the time. Okay. At the top of its path here, the peak of its path, it has all potential energy. As it reaches the lowest point on this path possible, even though it's a little bit off the ground, it's reached its lowest point, which means it has all kinetic. So we have to kind of determine where its lowest point is. At that lowest point, it will have all kinetic energy. As it climbs between the two, we have both potential and kinetic. Okay? So even as it starts to move and it's right here, so let's say we're looking at a spot on the path that's about right here. Does that have more potential energy or more kinetic energy? More potential, right? It's barely moving. It's still pretty high off the ground. It's got mostly potential. As it slides down to here, not quite at its lowest point yet, but still in motion, does it have both types? And what does it have a majority of, kinetic or potential? It has a majority of kinetic. Okay, so we need to understand that kind of slippery slope between kinetic and potential energy and what that looks like. Okay? Let's go ahead and try one here with our roller coaster. Okay, and it might be helpful for you to label these, kind of draw that roller coaster path on your sheet too and do those labels. It just goes A, B, C, D, E, F. Okay, and that's just to kind of help you pinpoint where that is on the roller coaster. All right, so this asks us if it moves from point A to point B, so it starts here at its lowest point, and it moves up to point B, is it gaining potential energy or gaining kinetic energy as it reaches its highest point? Gaining potential as it moves up. So we want to know what's the gravitational potential energy at point B relative to point A. So at point B, we want to find the gravitational potential, so we're going to do mgh. The mass of our roller coaster is 1,000 kilograms. Gravity we know is 9.8, and the height is 10. Okay, here we don't need to use the negative 9.8 because we're not falling, we're not looking at something that's going in the downward direction. We're just looking at the value of gravity. Okay, so you don't have to use the negative there. So our potential energy is equal to good, 98,000. And what's our units for energy? Joules, good. So both potential and kinetic energy have the unit joules. Good. Power is what has a unit for watts. Very good. Any questions here about just this part? That's pretty simple. Now we're going to take it a little bit further here. Oops. Now I want to look at if it goes from point B. Oh my. Okay, so our runner runs up the stairs. It only takes him 4 seconds, but he climbs a height of 4.5 meters. And this is what we're going to do in our lab today. We're going to look at the power output as we go upstairs. So here, he's doing work to overcome gravity by climbing those stairs. So we're still going to find his work done by the change in potential energy, and we're still going to find his power by taking that, how much time it took him to do that. Okay, so our mass is 70, time is 4, and our height is 4.5. Okay, so we can also find power by looking at the potential energy or the work done by this guy to overcome gravity, which is mgh over t. Okay, so that's another equation for power that we can use. He is exerting work, he's exerting power to overcome gravity by climbing those stairs, so we can use this equation here for power. Okay. So his power is mass times gravity times the height over the time it took him to climb those stairs. What'd you get? 771.75 watts. Good. Very good. Questions here? That's another equation for power that we can use. That's for climbers. Those are things that go up. Okay? We can find power in kinetic energy by things that are just traveling point A to point B. This equation for power is when something is climbing, when something's going up, okay, when we're overcoming gravity. Okay, how much energy did he have to expel to complete this task? So when we want to find energy, we're going to look at basically just the top of our power equation. Okay, power is equal to mgh over time. Okay, if we're looking at energy, we can just look at how much he exerted to overcome that gravity. What did he gain in potential energy as he climbed up those stairs? Okay, so we can look at 70 times 9.8 times the height. Okay, and we use this value because as he climbs the stairs and he reaches the top, he has gained this much potential energy. Okay, and that's how we look at that. Which I got 3,087 joules for that value. Okay? Do we understand why we're just using that equation for energy? Okay. All right, I want you to just try this one last problem, and I want you to try it by yourself. Okay, a climber takes a 122-meter climb. It takes him 4 minutes, 25 seconds. We want to find his average power output. Average power output is just power, like we've been solving for. So if it asks for average, that's okay. Okay, we're just solving for power like we know how.